The Hubble Space Telescope captured something in late December that violates the fundamental rules of how comets are supposed to work. We're watching powerful streams of gas and dust erupting from regions that should be completely dead, locked in darkness, frozen solid, utterly silent. This isn't a minor anomaly. 3I Atlas behaving in ways that challenge decades of established cometary physics. Between December 12th and December 27th, Hubble watched it do something that scientists are now calling deeply puzzling. Jets that should have shut down when their source regions rotated into shadow kept firing. They didn't just flicker weakly, they maintained structure, direction, and activity as if nothing had changed. Think about what that means for a moment. Comets operate on a simple principle. Sunlight hits ice. Ice turns to gas. Gas escapes, creating jets. No sunlight means no heat. No heat means no gas. No gas means no jets. It's one of the most reliable processes in planetary science, observed thousands of times across hundreds of comets. It's textbook physics. 3I Atlas is rewriting that textbook. Stay with me, because in the next several minutes we're going to walk through exactly what Hubble saw during those December observations, why multiple spacecraft had to confirm this wasn't a mistake, and what one of Harvard's most prominent astronomers thinks is really happening here. We're going to examine the rotation mystery that reveals structural complexity no one anticipated. We'll explore the physics problem that has researchers building entirely new models to account for shadowside activity. And we'll look at what this means, not just for this one object, but for our understanding of everything wandering through interstellar space. This isn't speculation, this isn't hype. This is hard data from the most advanced space telescope humanity has ever built, showing us something that demands explanation. The images exist, the jets are real, the impossibility is documented. But first, if you're as captivated by this mystery as I am, hit that like button right now. Drop a comment and tell me where you're watching from, because this discovery is unfolding in real time across the entire planet, and I want to know which part of Earth you're following this story from. Subscribe if you want to stay with this investigation as more data comes in. Let's go deeper. When Hubble turned its instruments toward 3I Atlas in December, scientists expected routine observations. They wanted to track the comet's activity as it passed through the inner solar system, measure the brightness of its jets, calculate the rotation period, and document how it compared to other comets. Standard procedure. Nothing controversial. What came back from those observations was anything but routine. The images showed a double-jet configuration, two distinct streams of material shooting in opposite directions from the nucleus. One jet was bright and strong. The other was fainter, weaker, but clearly present. Both were active. Both were releasing gas and dust into space at measurable rates. And here's where the story takes its first strange turn. The geometry didn't add up the way it should have. 3I Atlas had passed perihelion on October 29th, reaching its closest point to the Sun. Before perihelion on October 29th, one hemisphere of the nucleus faced the Sun directly, receiving maximum heating. That hemisphere lit up with activity, exactly as expected. In the weeks following perihelion, the object's rotation carried that formerly sun-facing hemisphere into shadow. It should have gone dark. It should have frozen. The jets originating from that region should have ceased. They didn't. Avi Loeb, former chair of Harvard's astronomy department, and one of the most credible voices in the study of unusual astronomical objects, examined the December images carefully. He noted something that didn't fit standard models. The weaker jet appeared to be coming from the hemisphere that should now be experiencing its winter, rotated away from solar heating, plunged into prolonged darkness. Yet it was still producing a visible jet. Loeb used specific language in his analysis. He called it extremely puzzling. He noted that the jets shift and wobble in unexpected ways. When a scientist of Loeb's caliber uses words like that, it's worth paying attention. This isn't sensationalism. This is a researcher with decades of experience looking at data that doesn't conform to established patterns. The December observations captured 3I Atlas at two key moments, December 12th and December 27th. That 15-day gap is significant because it's roughly equal to the object's rotation period. Between those two imaging sessions, the comet completed nearly one full rotation. Scientists could compare the jet positions and see how they'd shifted. They could track which features remained active and which changed. What they saw was consistency, where there should have been change. The shadowside region kept producing its jet. The activity didn't fade, the structure didn't collapse. Whatever was driving that jet wasn't dependent on direct sunlight, in the way standard cometary physics predicts. Now, before we go further, it's important to understand what we're not saying here. We're not claiming this is artificial. We're not jumping to exotic explanations. We're simply acknowledging that the observations show behavior that current models don't fully account for. That's not a crisis. it's an opportunity. It means nature is more complex than our current understanding captures, and that complexity is worth investigating. Science advances by finding the edges of what we know and pushing past them. 3. iAtlas is giving us one of those edges. The implications ripple outward in multiple directions. If interstellar comets can maintain activity on shadowed surfaces, it suggests internal processes or compositions that differ from what we see in solar system comets. It suggests that objects formed around other stars, in different chemical environments, might have properties we haven't encountered before. It suggests that the simple models we use to predict cometary behavior might need significant refinement when applied to visitors from beyond. And it raises questions we can't yet answer. Where is the energy coming from? Is there heat stored somehow in the interior? Are there volatiles so sensitive that they sublimate even in shadow? Is the structure more complex than a simple ball of ice and rock? Does rotation play a role we haven't considered? These questions aren't philosophical, they're practical. Answering them requires more data, better models, and careful analysis. The scientific community is engaged in that work right now, and the December Hubble images are the foundation they're building on. But here's what makes this moment particularly compelling. We're not waiting years for answers. Observations are ongoing. Multiple spacecraft watch 3 iAtlas from different angles. Ground-based telescopes are tracking it as it moves away from the Sun. Spectroscopic data is being analysed to determine what molecules are in those jets. Computer models are being built to test various internal structures and compositions. The investigation is active. The mystery is being pursued in real time, and we get to watch it unfold. That's the privilege of living in this era of astronomy. We have instruments sensitive enough to capture details across billions of kilometers. We have scientists dedicated to interpreting what those instruments reveal. And we have the means to follow along to understand the process to see how discovery actually happens. The December images are more than just pretty pictures from space. They're evidence. They're data points that need explaining. They're the start of a story that will take months or years to fully tell. So let me bring you into that story properly. Because what Hubble saw in those 15 days between December 12th and 27th is worth understanding in detail. And that detail is where the real strangeness emerges. When Hubble's Wide Field Camera 3 locked onto 3 Atlas on December 12th, it captured more than just an image. It captured a moment in the life of an object that has travelled incomprehensible distances to reach our corner of the galaxy. The telescope's instruments recorded the light being reflected and emitted from the comet's coma, the vast cloud of gas and dust that surrounds the solid nucleus at the centre. What appeared in that image was structure, not just a fuzzy blob but distinct features. 2 jets were clearly visible, streaming away from opposite sides of the nucleus. One was strong and bright, dominating the coma. The other was fainter but unmistakably present, shooting in the opposite direction. This double jet configuration told scientists immediately that the nucleus wasn't a perfect sphere uniformly releasing gas. It had active regions, specific vents or fissures on the surface where volatiles were escaping. 15 days later, Hubble looked again. The object was still there, still active, but the pattern had changed. The jets had rotated. They'd shifted position relative to the background stars, confirming what scientists suspected. This object was tumbling through space with a rotation period of approximately 15.5 hours. Every rotation brought different parts of the surface into sunlight and plunged others into shadow. Every rotation should have created a cycle of activity and dormancy as different regions heated and cooled. But that's not what the images showed. The December 27th observation revealed something unexpected. The jets were still active, but their geometry had changed in a way that shouldn't have been possible under standard cometary physics. 2 months after perihelion, the orientation of the nucleus relative to the Sun had shifted. The hemisphere that had faced the Sun during approach in late October, the one receiving maximum solar heating and producing the strongest jet, had now rotated into shadow by December. It was experiencing its night cycle, and that night should have lasted for hours as the object spun. Yet jets from that region continued to fire. Avi Loeb analysed both sets of images carefully. He measured the positions of the jets. He calculated their intensity. He compared the before and after states to understand how the activity had evolved. What he found was continuity, where there should have been interruption. The weaker jet, which appeared to originate from the formerly sunlit hemisphere, hadn't shut down when that region rotated away from the Sun. It had persisted. This is where the physics becomes important, because comets aren't mysterious objects. We understand them well. They're mixtures of water ice, frozen carbon dioxide, frozen carbon monoxide, dust particles, and organic compounds, all packed together in chunks ranging from hundreds of meters to tens of kilometers across. When these objects approach a star, the increase in solar radiation heats the surface. The ices don't melt in the traditional sense. They sublimate, transform directly from solid to gas without passing through a liquid phase. That gas expands rapidly, escaping from the surface and carrying dust particles along with it. These expanding gases form the visible jets. The jets feed the coma. The coma gets pushed by solar wind and radiation pressure, forming the characteristic tail that makes comets so visually striking. It's an elegant, well-understood process driven entirely by solar energy. The critical detail is this: no sunlight means no sublimation. When a region rotates into shadow, it cools. The surface temperature drops rapidly. The ices stop sublimating. The jets shut down. This cycle repeats every rotation: dayside active, nightside quiet. It's as predictable as day and night on Earth. 3I Atlas was breaking that cycle. The December images showed clear evidence that jets were active from regions that should have been too cold to produce them. The thermal energy required to sublimate ice and drive visible jets wasn't supposed to be present on a shadowed surface that had been out of direct sunlight for hours, yet the jets existed. They were measurable. They were real. Loeb described the situation carefully in his published analysis. He noted that the double jet configuration could indicate asymmetric outgassing. Perhaps one hemisphere has a higher concentration of volatiles than the other. That would be normal. Many comets show preferential activity from certain regions due to variations in compositional structure. But what wasn't normal was the persistence of activity after those regions rotated into darkness. The images also revealed something about the jet strength and morphology. The strong jet maintained its brightness, as expected for a region receiving direct or reflected sunlight. But the weak jet, the one from the shadowed hemisphere, didn't fade as much as it should have. It remained visible, structured, and directional. It wasn't just residual gas dissipating from earlier activity. It was fresh material being actively released from the surface. This distinction matters. When jets shut down, the gas they've already released continues to expand and dissipate for a while. You can see a fading afterglow of previous activity, even after the source has stopped. But what Hubble captured looked different. The jet structure suggested ongoing emission, not just the ghost of earlier outgassing. Scientists began asking questions. Could there be super volatile materials on the surface, compounds that sublimate at extremely low temperatures? Substances like carbon monoxide or methane can remain active at temperatures where water ice stays frozen. Perhaps 3I Atlas has a higher proportion of these supervolatiles than typical solar system comets. That would explain some level of continued activity in shadow. But even that explanation has limits. Supervolatiles require some heat to sublimate at visible rates. A completely frozen surface in total darkness shouldn't produce strong structured jets regardless of composition. There has to be an energy source, and if that source isn't direct sunlight, then where is it? This is the question the December observations forced into the open. It's not a rhetorical question or a mystery for mystery's sake. It's a practical problem that requires a physical answer. Energy doesn't appear from nothing. If jets are active, something is providing the energy to drive them. Some scientists suggested thermal inertia, the idea that the nucleus retains heat from its sun-facing period and releases it slowly as it rotates into shadow. This happens to some degree with all rotating bodies. Earth's surface doesn't cool instantly when the sun sets. Rocks and soil release stored heat gradually through the night. Perhaps the nucleus of 3I Atlas has properties that allow it to retain heat more effectively than expected. But there are problems with that explanation. The rotation period is 15.5 hours. Half of that, roughly 8 hours, is the time any given surface region spends in shadow during each rotation. For thermal inertia to drive jets over that entire period, the surface would need exceptional insulating properties. It would need to hold on to heat in the vacuum of space, where radiative cooling is efficient and relentless. Moreover, 3I Atlas spent millions or billions of years in interstellar space before entering our solar system. Any internal heat from its formation, or from previous stellar encounters, would have radiated away long ago. The only recent heat source is our Sun, and that heat should dissipate quickly when surface regions rotate into shadow. Other scientists propose subsurface reservoirs of volatiles. Perhaps the nucleus isn't a uniform block of ice and rock. Perhaps it has internal pockets, voids or cavities where gases accumulate under pressure. When cracks or fissures open due to thermal stress, these pockets release their contents explosively, creating jets regardless of whether the immediate surface is in sunlight. This is plausible. We know that comets can have complex internal structures. They're not monolithic. They're collections of smaller pieces loosely bound by gravity and ice, often with gaps and voids between fragments. These internal spaces could trap volatiles that remain pressurized even when the surface cools. But this explanation also requires specific conditions. It requires fractures that connect the subsurface reservoirs to the surface. It requires that those fractures remain open long enough for gas to escape. It requires explaining why the jets are so directional and consistent, rather than sporadic and chaotic. The December images don't resolve these questions. They document the phenomenon, shadow-side jets that shouldn't exist but clearly do. They provide the data point that demands explanation. The actual explanation will require more observation, more analysis, and probably some creative thinking about cometary structure and composition. What the images do prove is that 3I Atlas isn't behaving like a simple, well-understood comet. It has complexity. It has characteristics that push the boundaries of current models, and that complexity is teaching us something important. Interstellar objects might not conform to the patterns we've established by studying only solar system comets. This is the value of visitors from beyond. They bring new data. They challenge assumptions. They force us to question whether what we think we know is actually universal or just locally true. 3I Atlas is fulfilling that role perfectly, and the December observations are the clearest evidence yet that this object deserves intense scrutiny. As Hubble watched those jets shift and wobble over 15 days, it was documenting behavior that will be studied for years to come. Every frame of data is precious. Every measurement constrains the possible explanations. Every detail brings us closer to understanding what this object really is and why it's behaving the way it does. And as we're about to see, the physics problem this creates is deeper and more fascinating than the images alone suggest. To fully appreciate why the shadow-side jets are so troubling to scientists, we need to understand the physics of comets at a fundamental level. It's not enough to say comets are icy. We need to understand what happens to that ice when conditions change, and why those changes should produce predictable results. Comets are ancient. They formed billions of years ago in the outer regions of stellar systems, where temperatures are low enough for volatile compounds to freeze. Water, carbon dioxide, carbon monoxide, ammonia, methane. All of these exist as solid ices at the frigid temperatures found far from stars. Mixed with dust and rocky particles, these ices accumulate into larger and larger chunks through collisions and gravitational attraction. Eventually, you get objects ranging from a few hundred meters to several kilometers across. These objects remain frozen as long as they stay in the cold outer regions, but occasionally gravitational interactions kick them inward. They fall toward their parent star. As they do, they warm up. The warming isn't gradual and gentle. It's driven by solar radiation, which follows an inverse square law. Get twice as close to the sun, and the heating increases by a factor of 4. Get 10 times closer, and the heating increases 100-fold. As a comet plunges inward, the surface temperature rises rapidly. When the surface temperature reaches a certain threshold, the ices begin to sublimate. Water ice starts sublimating appreciably at temperatures around 200 degrees Kelvin, cold by Earth standards, but warm enough for the phase transition from solid to gas. Carbon dioxide sublimates at even lower temperatures. Carbon monoxide is even more volatile, transitioning at temperatures that would keep water ice rock hard. The gas produced by sublimation doesn't just sit on the surface, it expands, it pushes outward, escaping into the vacuum of space. As it escapes, it drags dust particles along with it. This process creates the jets we observe, focused streams of gas and dust erupting from active regions on the surface. Here's the critical point. This entire process is driven by solar heating. The energy to break the molecular bonds holding the ice together comes from photons, particles of light striking the surface. Without those photons, without that energy input, sublimation stops. Now imagine what happens as the comet rotates. A region on the surface starts in darkness. It's cold, perhaps just a few tens of degrees above absolute zero. As rotation brings it into sunlight, photons begin hitting it. The surface warms. Eventually it reaches the sublimation temperature for whatever ices are present. Jets begin. Gas and dust stream away. The region is active, but rotation continues. Eventually that same region rotates back into shadow. The photons stop arriving. The energy input ceases. The surface cools rapidly through radiative emission, infrared radiation carrying heat away into space. The temperature drops. Sublimation slows and then stops. The jets shut down. This cycle should repeat every rotation. Active, dormant, active, dormant. The timing depends on the rotation period and the geometry of the orbit, but the pattern is universal. Solar heating drives activity. Absence of solar heating ends activity. 3I Atlas is violating this pattern. The December observations show jets persisting from regions that had rotated into shadow. These aren't residual plumes from earlier activity. The structure and directionality of the jets suggest active, ongoing sublimation. Something is providing energy to drive gas production on a surface that isn't receiving direct sunlight. Scientists have proposed several possibilities, but each comes with complications. First, thermal inertia. Some materials absorb heat during the day and release it slowly over time. On Earth, this is why deserts can remain warm well into the night. The sand stores solar heat and releases it gradually. Perhaps the surface of 3I Atlas has high thermal inertia, allowing it to stay warm enough to drive sublimation even after rotating into shadow. But there are limits to this mechanism. The vacuum of space is an excellent insulator in one sense. There's no air to conduct heat away, but it's also merciless. A surface radiates heat directly into the cosmos through infrared emission. Without a continuous energy input, temperatures fall rapidly. For thermal inertia to maintain sublimation for hours, the surface would need extraordinary heat retention properties. Moreover, 3I Atlas spent an unimaginable span of time in interstellar space before reaching our solar system. The cold of the interstellar void is profound. Any primordial heat from the object's formation would have radiated away eons ago. The only recent heat source is our Sun, and we're talking about maintaining that heat through an 8-hour shadow period during each rotation. The numbers don't favour simple thermal inertia as a complete explanation. Second possibility, subsurface volatiles. Perhaps the nucleus isn't just a solid ball of ice. Perhaps it has layers. Perhaps there are pockets beneath the surface where highly volatile ices are trapped. When thermal stress fractures the surface, these subsurface reservoirs vent their contents, creating jets independent of whether the immediate surface is in sunlight. This explanation is more plausible. We know comets aren't uniform. They're likely rubble piles, collections of smaller fragments weakly bound together. Internal voids are not only possible but probable. These voids could trap gases that remain under pressure even when the surface cools. But this raises new questions. Why are the jets so consistent and directional? Random venting from fractures should produce sporadic, chaotic behavior. The December images show structured jets that maintain their orientation relative to the nucleus. That suggests fixed vents or channels, not random breaks in the surface. It also requires explaining how those subsurface reservoirs got filled in the first place. Did solar heating during the approach to perihelion drive gases into internal cavities? If so, why are they releasing now after perihelion rather than during peak heating? The timing seems backwards. Third possibility, supervolatile ices. Carbon monoxide and methane sublimate at much lower temperatures than water. Perhaps 3I Atlas has a higher concentration of these compounds than typical solar system comets. Perhaps the shadowed regions are releasing these supervolatiles while water ice remains frozen. This could work. If the composition is unusual, if this object formed in a stellar environment richer in carbon compounds, just for example, then the volatile budget could differ significantly from what we see in solar system comets. Supervolatiles could maintain activity at temperatures that would keep water ice dormant. But even supervolatiles need some heat. Carbon monoxide doesn't sublimate vigorously at absolute zero. There's still an energy requirement, just at a lower threshold. And the jets would need to be rich in these compounds for them to produce visible activity. Spectroscopic observations should reveal this if it's the explanation. Fourth possibility, something unexpected. A process or mechanism we haven't fully considered. This is the catch-all that scientists invoke when known mechanisms don't quite fit. It's not a satisfying answer, but it's intellectually honest. The universe has surprised us before with phenomena that required new physics to explain. Could there be chemical reactions occurring inside the nucleus? If reactive compounds remain separated during the long interstellar journey, solar heating during perihelion could trigger reactions that generate heat. That heat could then drive sublimation from within, independent of surface temperature. Could there be radiative heating from the coma itself? The gas and dust surrounding the nucleus absorb sunlight and re-emit it as infrared. Could this infrared radiation illuminate the shadowed regions enough to maintain low-level sublimation? It's a weak effect, but over hours perhaps it could contribute. Could the rotation itself play a role? Centrifugal forces from the spin could stress the surface, opening fractures that release trapped volatiles. It's not a strong force on an object this size, but combined with thermal expansion and contraction, it could be significant. None of these explanations alone is fully satisfying. The reality might be a combination. Thermal inertia plus subsurface volatiles plus supervolatile ices all contributing to shadowside activity. Science rarely delivers single, simple answers to complex questions. Nature tends to be multivariate, with several factors working together, But that's exactly what makes this discovery compelling. The December images have shown us behavior that doesn't fit neatly into our existing framework. They've revealed complexity that demands investigation. They've given us a puzzle that will require careful analysis, creative modelling, and probably some surprises along the way to solve. And that process is underway right now, driven by one of the most thoughtful and fearless astronomers working today. When Avi Loeb looks at astronomical data, he sees both what's there and what's missing. He examines the evidence carefully, measures it against established theories, and then, critically, he asks whether those theories are sufficient to explain what's being observed. It's this willingness to question assumptions that makes his analysis of the December Hubble images particularly valuable. Loeb isn't a sensationalist. His credentials are extensive, and his work is deeply grounded in rigorous physics. He formerly chaired Harvard's astronomy department. He founded the Black Hole Initiative. He's published hundreds of peer-reviewed papers on topics ranging from cosmology to the search for extraterrestrial intelligence. He understands the scientific method intimately, and he applies it consistently. But he also understands that science advances by confronting anomalies, not by explaining them away prematurely. When data doesn't fit existing models, the appropriate response isn't to force-fit the data into the models, it's to ask whether the models need refinement. His analysis of 3i Atlas began with the basic observations. 2 jets, opposite directions, rotating with the nucleus. The strong jet pointed one way, the weak jet pointed the other. The rotation period of approximately 15.5 hours meant the jets appeared to wobble from Earth perspective, as different surface features came into view and then rotated out of sight. This much was expected. Many comets show similar behavior. The wobbling is just geometry, our viewing angle changing as the object spins. Nothing mysterious there. But Loeb noticed something else in the December images. The weak jet appeared to be coming from the hemisphere that had been sun-facing during the approach to perihelion, but was now rotated into shadow post-perihelion. That hemisphere should have gone dormant. The jets from that region should have shut down. They hadn't. In his published analysis on Medium, Loeb described this as extremely puzzling. He noted that the jets shift and wobble in unexpected ways. The word choice is deliberate. Puzzling acknowledges that current understanding doesn't fully account for the observations. Unexpected signals that the behavior deviates from predictions. Loeb has experience with interstellar objects that defy simple explanation. He spent years analysing Oumuamua, the first confirmed interstellar visitor detected in our solar system. That object showed non-gravitational acceleration. It was being pushed by something other than gravity. The most likely explanation was outgassing, like a comet, but no jets were visible and no coma was detected. Oumuamua became controversial when Loeb suggested that one possible explanation, however unlikely, was that it could be artificial. A light sail pushed by radiation pressure would show exactly the trajectory Oumuamua displayed. The hypothesis was highly speculative, but Loeb argued it deserved consideration alongside natural explanations. The scientific community largely disagreed. Most researchers favour natural explanations for Oumuamua, suggesting it was a comet with extremely low volatile content or an unusual shape that caused asymmetric outgassing invisible to our instruments. But the debate highlighted an important principle. Extraordinary observations deserve thorough investigation of all possibilities, even uncomfortable ones. Loeb's willingness to consider unconventional explanations stems from this principle. He doesn't claim 3 Atlas is artificial. He simply argues that when an object behaves in ways that challenge our models, we should expand our thinking, not just our models. With 3i Atlas, Loeb focused on what the December images actually showed. The persistence of the shadowside jet suggested either an internal energy source or a composition radically different from typical comets. He outlined several scenarios. First, subsurface volatile reservoirs. If the nucleus has internal cavities filled with pressurized gas, those cavities could vent through surface fractures regardless of whether the immediate surface is heated by sunlight. This would require a specific internal structure, not a solid block, but a porous or fractured interior with pathways for gas to escape. Second, supervolatile ices. If 3i Atlas contains a high proportion of carbon monoxide or other compounds that sublimate at very low temperatures, those ices could remain active even on shadowed surfaces. This would suggest the object formed in a chemical environment different from our solar system's outer regions. Third, thermal anomalies. Perhaps the material properties of the nucleus allow it to retain heat more effectively than typical comet ices. This could be due to composition, structure, or both. If the surface has insulating layers with heat-retaining materials beneath, warmth from solar heating could persist for hours as the surface rotates into shadow. Loeb emphasized the need for spectroscopic data. By analyzing the light coming from the jets, scientists can identify which molecules are present. Different compounds have unique spectral signatures, specific wavelengths they absorb or emit. If the shadow-side jet shows high concentrations of supervolatiles like carbon monoxide, it would support the composition hypothesis. If the spectrum matches water-rich outgassing, it would suggest heat retention or subsurface reservoirs. He also called for continued observation. 3I Atlas is moving away from the Sun now, gradually fading as it recedes. As solar heating decreases, the jets should weaken. Monitoring how quickly they decline will constrain the energy mechanisms driving them. If they persist longer than solar heating alone would predict, it strengthens the case for internal heat sources. What makes Loeb's analysis particularly valuable is his intellectual honesty. He doesn't claim to know the answer. He presents observations, outlines possible explanations, and identifies what additional data would help distinguish between them. This is science at its best, acknowledging uncertainty while systematically working to reduce it. But Loeb also does something else. He contextualizes 3I Atlas within the broader question of interstellar object diversity. We've now observed 3 confirmed visitors from beyond our solar system. Each one has been surprising in different ways. Oumuamua showed unexplained acceleration without visible jets. 2A Borisov looked like a normal comet, reassuringly familiar. Now 3I Atlas shows jets from regions that shouldn't be active. This pattern, initial surprise, partial familiarity, new surprises, suggests that interstellar space contains a wider variety of objects than our solar system represents. Different stellar systems have different chemistries, different formation histories, different dynamical processes. The objects they produce and eject might not conform to templates based solely on solar system examples. Loeb argues this diversity is exactly what we should expect. The galaxy contains hundreds of billions of stars. Most have planetary systems. All eject small bodies into interstellar space through gravitational interactions. The inventory of objects drifting between stars is vast and likely includes types we haven't yet encountered in our own system. Each interstellar visitor is therefore precious, a direct sample of material formed around another star, delivered to our doorstep for close examination. We don't have to travel light years to study these objects. They come to us. The challenge is detecting them, observing them before they leave, and extracting maximum information from fleeting encounters. 3I Atlas represents one of those precious opportunities. The December images captured by Hubble are data we'll analyze for years. They document behavior that will inform theoretical models and constrain our understanding of cometary physics. They show us nature doing something we didn't fully predict, which means nature has more to teach us. Loeb's analysis brings scientific rigor to that teaching process. By carefully examining the evidence, proposing testable explanations, and calling for additional data, he's advancing our understanding methodically. The mystery isn't solved yet. The shadow-side jets remain puzzling, but the path toward explanation is clear. More observation, better models, and openness to the possibility that our current understanding is incomplete. And that path is being walked by more than just Hubble. Multiple spacecraft turned their instruments toward 3I Atlas, each adding unique perspectives that deepen our understanding. Hubble wasn't alone in its scrutiny of 3I Atlas. This interstellar visitor attracted the attention of multiple NASA missions, each offering perspectives impossible from Earth and collectively building a far more complete picture than any single observatory could provide. The Parker Solar Probe, humanity's most daring solar mission, reportedly observed 3I Atlas during a period when Earth-based telescopes were effectively blind. As the comet approached perihelion, it entered the region of intense solar glare. From Earth's vantage point, it was like trying to spot a candle flame next to a searchlight. The sun's overwhelming brightness made observations impossible, but Parker was already inside that zone of brightness. Launched to study the sun's corona and solar wind, Parker orbits closer to our star than any spacecraft in history. Its heat shield protects delicate instruments from temperatures exceeding 1,000 degrees, while its cameras peer outward into the inner solar system. Around the time of perihelion in late October, Parker's Whisper instrument reportedly captured images of 3I Atlas as the comet made its closest approach to the Sun. These observations are invaluable for several reasons. First, they documented the comet during peak solar heating, when activity should be at maximum. The jets visible in Parker's images represent the baseline, the full-strength outgassing driven by intense solar radiation at close range. This baseline is what scientists compare to later observations to understand how activity evolves with distance and geometry. Second, Parker's vantage point was completely different from Earth's. While ground-based telescopes and Hubble see 3i Atlas from one angle, Parker saw it from a position much closer to the Sun, looking outward. This geometric difference allows researchers to reconstruct the three-dimensional structure of the jets. Jets that appear faint from one angle might be bright from another. Features hidden by geometry from Earth become visible from Parker's perspective. Third, Parker's high-cadence imaging, multiple observations per day, revealed how quickly the jets respond to changes in solar heating. As 3i Atlas rotated, different regions faced the Sun. Parker watched those regions light up and dim with each rotation, documenting the thermal cycle in unprecedented detail. The data Parker collected serves as ground truth. When scientists later compare Hubble's December images to Parker's perihelion observations, they can measure exactly how much the jets declined after peak heating. They can determine whether the decline matches theoretical predictions or whether something unexpected is happening. The fact that shadow-side jets remain visible in the Hubble images despite being weeks past perihelion becomes even more striking when compared to Parker's images. The contrast is stark. During perihelion, jets should be at maximum strength. Weeks later, after rotating into shadow, they should be minimal or absent. Instead, they're still visible and structured. Meanwhile, NASA's Europa Clipper spacecraft, currently on its way to study Jupiter's icy moon, turned its instruments toward 3i Atlas in mid-December. The spacecraft carries an ultraviolet spectrograph designed to study Europa's tenuous atmosphere and analyze its surface ice composition. This same instrument is perfectly suited for studying cometary emissions. Ultraviolet spectroscopy reveals information invisible to optical cameras. Different molecules absorb and emit ultraviolet light at specific wavelengths. Water vapor, carbon dioxide, carbon monoxide, ammonia, each has a unique UV signature. By analyzing the spectrum of light coming from 3i Atlas's jets, Europa Clipper could identify which molecules were present and in what proportions. This compositional data is critical for testing hypotheses about the shadow-side jets. If the jets contain large amounts of super-volatile ices like carbon monoxide, it would support the idea that unusual composition explains their persistence. If the spectrum shows primarily water vapor, it would suggest heat retention or subsurface reservoirs instead. NASA hasn't released detailed spectroscopic results from Europa Clipper yet, but the mere fact that the mission devoted observing time to 3i Atlas speaks volumes. Europa Clipper is a flagship mission worth billions of dollars, optimized for studying Jupiter's moon. Redirecting its instruments to observe a passing comet isn't done casually. It signals that scientists at the highest levels recognize 3i Atlas as an object of exceptional interest. The coordination among these three spacecraft, Parker, Hubble, and Europa Clipper, represents modern astronomy at its best. Each instrument has unique capabilities, each occupies a different position in space. Together, they provide complementary data that no single observatory could capture. Parker gives us the perihelion baseline and an inner system perspective. Hubble provides high-resolution visible light images that track jet evolution over time. Europa Clipper delivers compositional analysis through ultraviolet spectroscopy. Synthesizing these datasets creates a comprehensive picture of 3i Atlas's behavior. This kind of coordinated campaign happens only for targets of exceptional scientific value. NASA doesn't casually redirect multiple flagship missions. The decision to observe 3i Atlas with this array of assets reflects a collective recognition in the scientific community that interstellar visitors are rare opportunities that must be seized. We've only confirmed 3 interstellar objects passing through our solar system. The first, Oumuamua, was detected after it had already passed perihelion and was on its way out. Observations were limited by its faintness and rapid departure. The second, 2i Borisov, gave us more notice and was observed extensively, but it behaved largely as expected for a comet. 3i Atlas is different. It's bright enough for detailed study. It arrived with sufficient warning for mission planners to coordinate observations, and it's behaving in ways that challenge our models, making every data point precious. The multi-spacecraft observations ensure that what we're seeing is real. It's not an instrumental artifact, a glitch in Hubble's camera or a processing error. Multiple independent instruments from different vantage points are all telling the same story. The jets exist. They're active from shadowed regions. They maintain structure and directionality. This consensus across platforms transforms individual observations into confirmed phenomena. It moves the question from "is this real?" to "why is this happening?" And that's exactly where scientific investigation should focus, not on verifying basic observations, but on explaining mechanisms. As 3i Atlas continues to move away from the Sun, additional observatories will track it as long as it remains bright enough. Ground-based telescopes with spectroscopic capabilities will analyze its composition. Radio telescopes will search for any unusual emissions. Infrared observatories will measure its thermal properties. Each observation adds another piece to the puzzle. Each measurement constrains the possible explanations. Each data point brings us closer to understanding why this object is behaving the way it does. And at the heart of that behavior is a mystery that becomes even more fascinating when you examine exactly how 3i Atlas rotates. Every 15.5 hours, 3i Atlas completes one full rotation. This isn't particularly fast or slow by cometary standards. Some small bodies spin much faster, completing rotations in minutes. Others tumble slowly, taking days to complete a single turn. 15.5 hours is moderate, unremarkable in itself. What makes it remarkable is what that rotation reveals about the object's structure and behavior. The wobbling jets that Avi Loeb described are direct evidence of rotation. As the nucleus spins, the vents or fissures where jets originate rotate with it. From Earth's perspective, this makes the jets appear to sweep across the coma, like searchlight beams sweeping across the sky. They're not actually moving, the surface features anchoring them are fixed, but because those features are rotating, the jets appear to shift position. This phenomenon allows scientists to do something clever. By carefully tracking how the jets move relative to the background stars and measuring the time it takes for them to return to their starting positions, astronomers can calculate the rotation period precisely. The December images provided exactly this kind of data, confirming the 15.5-hour period. But rotation does more than just make jets wobble. It fundamentally affects how the nucleus interacts with sunlight and how heat distributes across its surface. Imagine a non-rotating comet approaching the sun. One hemisphere would face the sun continuously, heating to extreme temperatures. The opposite hemisphere would never see sunlight, remaining frozen at interstellar temperatures. You'd have a stark division, one side active, one side dead. Now add rotation. As the nucleus spins, every part of the surface eventually faces the sun. Heat distributes more evenly. Temperature extremes moderate. Instead of one permanently hot side and one permanently cold side, you get a cycle. Every region experiences periods of heating and cooling as it rotates through day and night. The rotation rate determines how extreme that cycle becomes. Fast rotation spreads heat more evenly, preventing large temperature differences between lit and shadowed regions. Slow rotation allows for greater extremes. Regions that face the sun for extended periods get very hot, while regions in prolonged shadow get very cold. At 15.5 hours, 3i Atlas falls into a moderate regime. Each surface region spends roughly 8 hours in sunlight and 8 hours in shadow during every rotation. This is enough time for significant heating during the day and substantial cooling during the night, but it's not so slow that you get wildly extreme temperatures, which makes the shadow side jets even more puzzling. With this rotation rate, shadowed regions should cool significantly. The surface would radiate away its heat through infrared emission into space. After hours in darkness, the temperature should drop well below the threshold for water ice sublimation. Jets should shut down, yet they persist. The December images show that the jets maintain not just minimal activity, but structured, directional outgassing. The weak jet isn't a sporadic sputter or a random puff of gas. It's a coherent stream, oriented consistently relative to the nucleus. That kind of structure suggests an active vent, a specific location on the surface where gas is escaping continuously. This implies something about the internal structure of 3i Atlas. Directional jets require channels or pathways that route volatiles to specific exit points. You don't get narrow, focused jets from uniform surface sublimation. You get them from concentrated vents, like nozzles, where subsurface pressure forces gas through restricted openings. That means 3i Atlas isn't a homogeneous ball of ice and rock. It has internal architecture. There are likely cavities beneath the surface, possibly interconnected, where volatiles accumulate. There are fractures or conduits that connect these cavities to surface vents. The whole system has structure and organization. How did that structure form? One possibility is thermal cycling. If 3i Atlas experienced previous close encounters with stars during its journey through the galaxy, repeated heating and cooling could have created layered structure. Surface ice sublimates during warm periods, leaving behind a dust-rich crust. Beneath that crust, ice remains protected. Over time, this creates a layered object with different properties at different depths. Another possibility is impact history. Comets collide with each other, with asteroids, with debris. Each impact fractures the interior, creating cracks and voids. These fractures become pathways for gas migration. The nucleus becomes a network of weakly bound fragments with gaps between them. or perhaps its original structure. When 3I Atlas formed in the protoplanetary disk of its home star system, it might have accreted as a rubble pile, countless smaller pieces sticking together through gentle collisions and ice sintering. That original structure would persist, making the object porous and fractured from birth. Any of these scenarios could explain why 3I Atlas has the internal complexity needed to produce directional jets, but they don't fully explain why those jets persist on shadowed surfaces. For that, you need not just structure, but an energy source or a volatile reservoir that remains active despite cooling. The rotation data provides one more clue. The jets don't maintain constant strength throughout the rotation. Parker's perihelion observations showed that jet brightness varies as different regions face the sun. The strong jet appears brightest when it's oriented toward the light source. As it rotates toward the edge of the nucleus from Earth's perspective, it dims slightly. This is partly geometry, we're seeing it at an angle, but it also suggests the jet responds to solar illumination. But the weak jet shows different behavior. It remains visible even when originating from regions that should be in shadow. Its brightness doesn't show the same dramatic variation with rotation. This suggests it's not driven primarily by direct solar heating. Something else, subsurface heat, trapped volatiles, supervolatile ices, is maintaining its activity. Scientists have started building computer models to test various internal structures. They simulate nuclei with different porosities, different layering schemes, different volatile distributions. They model how heat conducts through these structures as the surface rotates. They calculate where jets should form and how strong they should be. The goal is to find a model that matches the observations. If a simulation can reproduce the double jet configuration, the rotation-dependent brightness variations, and the persistence of shadow-side activity, then the assumptions built into that model are likely close to reality. This work is ongoing. Preliminary models suggest that a combination of factors is probably necessary. High porosity to slow heat loss, supervolatile ices concentrated in subsurface regions, fractures that connect those regions to specific surface vents. No single factor alone is sufficient, but several working together might explain what we're seeing. The rotation mystery, then, is really several interrelated mysteries. Why do the jets maintain structure? What internal architecture creates directional venting? Why does activity persist in shadow? And how did an object traveling through the frozen void of interstellar space develop such complex behavior? Answering these questions will take time, more data, and probably some surprises. But the questions themselves are valuable because they push our understanding forward. They force us to think more carefully about cometary structure, thermal dynamics, and the diversity of objects in the galaxy. And they remind us that every interstellar visitor has something new to teach. Step back from the specific details of jets and rotation for a moment. Zoom out to the bigger picture. What does 3I Atlas really tell us? Not just about one strange comet, but about the nature of interstellar objects, the diversity of the galaxy, and the assumptions we make about how the cosmos works. Before 2017, we had never confirmed a single object from beyond our solar system passing through our neighbourhood. We knew theoretically they must exist. Stars eject planetesimals through gravitational interactions. Those ejected bodies wander through interstellar space. Occasionally, one should pass through another stellar system. The math predicted it, but we'd never actually seen it happen. Then, Oumuamua arrived and changed everything. Its discovery was almost accidental. The Pan-STARRS telescope in Hawaii spotted an unusual object moving rapidly through the inner solar system. Initial observations suggested an asteroid, but its trajectory was wrong. It was moving too fast on a hyperbolic orbit that clearly originated from interstellar space. It had come from outside and it was passing through on its way back out. Scientists scrambled to observe it. Every major telescope that could see it was pointed at the object. The data that came back was puzzling. Oumuamua was elongated, possibly cigar-shaped or disc-like. It tumbled through space in a complex rotation. Most strangely, its trajectory showed non-gravitational acceleration. It was being pushed by something other than the sun's gravity. The most obvious explanation was outgassing. Comets accelerate when jets push against their surfaces, but Oumuamua showed no visible jets, no coma, no tail. It looked like an asteroid but moved like a comet. The contradiction sparked intense debate. Avi Loeb proposed that one possible explanation, however speculative, was that Oumuamua might be artificial. A solar sail, pushed by radiation pressure, would show exactly the trajectory observed. It was a controversial suggestion, met with skepticism by most of the scientific community. But it highlighted an important point. We were seeing something we couldn't easily explain with conventional models. Most astronomers still favour natural explanations for Oumuamua. Perhaps it was a comet with very low volatile content, producing jets too faint to detect. Perhaps its shape caused asymmetric reflection of sunlight that mimicked acceleration. Perhaps it was composed of exotic materials we haven't encountered before. All of these remain possibilities. Then came 2I Borisov, and everything seemed to normalise. 2I Borisov looked like a comet. It had a bright coma. It had a visible tail. Its spectroscopic signature showed water vapour and carbon-based compounds, exactly what you'd expect. It behaved according to established physics. Scientists breathed a sigh of relief. Okay, they thought. Oumuamua was unusual, but not every interstellar object is strange. Some are just normal comets from other stellar systems. Now 3I Atlas arrives, and the pattern of surprise reasserts itself. It looks like a comet, check. It has jets, check. It has a coma, check. But those jets are active from shadowed regions. The behaviour doesn't match standard models. The object is familiar enough to seem understandable, but strange enough to resist easy explanation. This sequence, strange, normal, strange again, is teaching us something profound. The universe is more diverse than our single solar system can represent. The processes that form and modify objects around other stars don't necessarily produce results identical to what we see around our Sun. Chemistry varies. Thermal histories differ. Structural evolution follows different paths. Think about what this means for exoplanet science. We've discovered thousands of planets orbiting other stars, and we've learned that planetary systems are wildly diverse. Hot Jupiters orbit closer to their stars than Mercury orbits our Sun, a configuration we never imagined before finding them. Super-Earths, rocky planets larger than Earth but smaller than Neptune, have no equivalent in our solar system. Tightly packed systems with multiple planets in orbits that would be unstable by our standards turn out to be common. This diversity forced astronomers to rethink planet formation. Theories based solely on our solar system were insufficient. New models had to account for planetary migration, different disk chemistries, and formation pathways we hadn't considered. Interstellar objects are bringing that same lesson to smaller bodies. Comets, asteroids, planetesimals, the building blocks of planetary systems, might vary more dramatically between stellar systems than we thought. Different stars have different elemental abundances. A star richer in carbon might produce comets with unusual carbon-to-oxygen ratios. A star with higher ultraviolet output might create different organic chemistry in its outer system ices. A binary star system might dynamically sculpt planetesimals in ways single stars don't. 3I Atlas might be showing us what a comet from a chemically distinct stellar environment looks like when it visits our Sun. Its volatiles might have different proportions than solar system comets. Its internal structure might reflect formation conditions that don't occur in our system. Its behaviour near our Sun might be our first glimpse of how foreign chemistry responds to solar heating. This has implications beyond just understanding comets. If we're going to interpret observations of exoplanets and make inferences about their compositions, atmospheres, and potential habitability, we need to understand the full range of materials and processes that occur in different stellar environments. Interstellar objects provide direct samples, actual material formed elsewhere, not just light from distant worlds. Every interstellar visitor is therefore precious. We can't yet travel to other stars. We can't yet sample exoplanet atmospheres directly. But when interstellar objects pass through our system, they bring samples to us. They're free probes from other stellar systems, and we should extract every bit of information we can from them. But there's another layer to this story, one that touches on questions humans have asked since we first looked up at the stars. Are we alone? Is our solar system typical? Does intelligent life exist elsewhere? Most scientists strongly favour natural explanations for unusual astronomical objects. The universe is vast and old. Nature has had billions of years to experiment with different configurations, compositions, and processes. The fact that we occasionally see something unexpected doesn't mean it's artificial. It usually means nature is more creative than our current models account for. But Avi Loeb asks a fair question. At what point does the accumulation of anomalies warrant considering hypotheses outside our conventional framework? When does unusual natural process become a less parsimonious explanation than something we haven't encountered before? He's not claiming 3I Atlas is artificial. He's arguing that the scientific method requires considering all hypotheses that fit the evidence, then testing them systematically. If an object shows behaviour that strains natural explanations, you don't immediately conclude it's artificial, but you also don't refuse to consider the possibility just because it's uncomfortable. History provides precedents. When pulsars were first discovered, Their precise radio pulses were so regular that they were jokingly called LGM signals, little green men. The precision seemed artificial. Turned out they were rapidly rotating neutron stars, a natural phenomenon but one that required new physics to understand. Nature was stranger than expected, not artificial. When quasars were discovered, their extreme brightness seemed to violate what we knew about galaxies and cosmology. They turned out to be supermassive black holes accreting matter, again natural but requiring expanded theoretical frameworks. In both cases, initial mystery led to deeper understanding of natural processes. That's almost certainly what will happen with 3I Atlas. The shadowside jets will eventually be explained through some combination of composition, structure, and thermal dynamics that we haven't fully characterized yet. But the process of investigation is valuable regardless of the conclusion. By refusing to prematurely close the question, by gathering comprehensive data, by building rigorous models, science advances. We learn more about comets, thermal physics, volatile chemistry, and the diversity of objects in the galaxy. And we remain open to genuine surprises. The universe has surprised us before. It will surprise us again. Maintaining intellectual humility, acknowledging that our current understanding might be incomplete, is essential for scientific progress. 3. iAtlas is providing that opportunity. The December images have shown us something that current models don't fully predict. Rather than dismissing it or explaining it away with hand-waving, scientists are taking it seriously. They're building better models. They're gathering more data. They're asking harder questions. That's exactly how science should work when confronted with anomalies, and that work is happening right now across multiple institutions and research groups worldwide. The mystery of the shadowside jets isn't being solved in a single lab or by a single scientist. It's being pursued by the global astronomical community through a coordinated effort involving observations, theoretical modeling, and data synthesis. This is modern science at its best, collaborative, rigorous, and transparent. The first priority is spectroscopy. Identifying exactly what molecules are in those jets will constrain their source and energy requirements. Every molecule has a unique spectral fingerprint, specific wavelengths of light it absorbs or emits based on its quantum structure. By analyzing the spectrum of light coming from 3I Atlas's coma and jets, scientists can determine composition with precision. Water vapor shows strong absorption and emission features in certain infrared and ultraviolet wavelengths. Carbon dioxide has a different signature. Carbon monoxide, methane, ammonia, each produces distinct patterns. By measuring which wavelengths are present and their relative intensities, researchers can calculate the abundance of each molecule. This compositional data directly addresses the key questions. If the shadowside jet is rich in super-volatile ices like carbon monoxide, it supports the hypothesis that unusual composition explains persistent activity. Carbon monoxide sublimates at much lower temperatures than water. If it's the dominant volatile, the jet could remain active even as surface temperatures drop. But if the spectrum shows water-dominant composition, it suggests different mechanisms. Water requires higher temperatures to sublimate at visible rates. If the shadowside jet is producing water vapor despite being on a cold, dark surface, then something is providing heat. Either thermal inertia is greater than expected, or subsurface reservoirs are releasing stored volatiles, or some other heat source is at work. Several observatories have devoted time to spectroscopic observations of 3I Atlas. Ground-based telescopes with high-resolution spectrographs have been tracking it. The data is being analyzed now, and results should appear in peer-reviewed journals over the coming months. These papers will detail the findings and propose explanations grounded in the actual measurements. Ground-based telescopes are also tracking 3I Atlas's brightness as it recedes from the Sun. As distance increases, solar heating decreases by the inverse square law. Get twice as far from the Sun, and the heating drops to 1/4. Get 3 times as far, and it drops to 1/9. The jets should weaken correspondingly. If the jets decline exactly as predicted by solar heating models, it suggests direct sunlight is the primary driver. But if they persist longer than expected, if they remain active at distances where solar heating should be too weak, it strengthens the case for internal heat sources or supervolatile materials. This kind of monitoring also reveals rotation effects over time. As we've discussed, the jets should vary in brightness as different regions rotate into and out of sunlight. Long-term monitoring tracks these variations, allowing scientists to map which parts of the surface are most active and how that activity evolves with time and distance. Rotation rate itself can change. If jets are strong enough, they push on the surface like tiny rocket engines, creating torque that alters the spin. This is what happened with Oumuamua, Its non-gravitational acceleration likely came from asymmetric outgassing creating thrust. If 3I Atlas shows changes in rotation rate, it would confirm that the jets are powerful enough to affect the object's dynamics, which constrains their mass flux and energy output. Interestingly, the Breakthrough Listen project observed 3I Atlas on December 18th. Breakthrough Listen is an initiative dedicated to searching for evidence of extraterrestrial technology, funded by the Breakthrough Initiatives and using major radio telescopes worldwide. They typically observe stars that might host habitable planets, listening for artificial radio signals. They observed 3I Atlas because its unusual behavior warranted checking. Using the Green Bank telescope in West Virginia, one of the most sensitive radio observatories on Earth, they scanned frequencies from 1 to 12 GHz, looking for any signals that might indicate technological origin. They detected nothing unusual. No artificial signals, no structured radio emissions, just the natural radio noise expected from solar-wind interactions and other astrophysical processes. This null result doesn't prove 3I Atlas is natural. Absence of evidence isn't evidence of absence. But it does place upper limits on potential signal strength. If the object were broadcasting radio signals, Breakthrough Listen would likely have detected them. The fact that no signals were found rules out certain exotic hypotheses while leaving natural explanations unaffected. The fact that Breakthrough Listen devoted observing time to 3 Atlas illustrates how seriously the scientific community takes unusual interstellar objects. The project's resources are limited. They can't observe everything. They prioritize targets based on scientific interest and the potential for discovering something genuinely new. 3I Atlas made that priority list because its behavior is anomalous enough to deserve investigation from multiple angles, including technosignature searches. Beyond observation, theoretical work is advancing rapidly. Astrophysicists are building sophisticated computer models of cometary nuclei with different internal structures, compositions, and thermal properties. These models simulate how heat conducts through porous ice-rock mixtures. They calculate how volatiles migrate from depth to surface. They predict where jets should form and how their strength should vary with solar distance and rotation. The models are complex. They have to account for thermal inertia, how materials absorb and release heat over time. They have to simulate sublimation physics, how phase transitions occur at different temperatures and pressures. They have to incorporate rotation, how spin distributes heat across the surface. And they have to handle internal structure, how voids, fractures, and layers affect heat flow and gas migration. Different research groups are testing different assumptions. Some models focus on composition, varying the ratios of water ice, carbon dioxide, carbon monoxide, and other volatiles. Others focus on structure, testing everything from solid nuclei to rubble piles with high porosity. Still others explore exotic scenarios, chemical reactions generating heat, radiogenic decay, or accumulated energy from cosmic ray bombardment. Each model makes predictions. If the composition is primarily water ice with standard solar system ratios, jets should shut down rapidly when surfaces rotate into shadow. If supervolatiles are dominant, jets should persist longer but show different spectral signatures. If the structure is highly porous, thermal inertia increases and heat retention improves. The predictions are then compared to observations. Models that match the data well are refined and tested against new observations. Models that fail to match are discarded or revised. This iterative process gradually narrows the range of possibilities, converging on explanations that are both physically plausible and consistent with measurements. Preliminary results from some models suggest that a combination of factors is necessary. High porosity helps retain heat. Supervolatile ices concentrated in specific regions provide low-temperature activity. Fractures connecting subsurface reservoirs to surface vents create directional jets. No single factor alone explains everything, but several working together create behavior consistent with what Hubble observed. This kind of multi-factor explanation is common in planetary science. Nature rarely delivers single-cause phenomena. More often, several processes interact, each contributing to the observed outcome. Untangling those contributions requires careful analysis and multiple independent measurements. That's why the coordinated observation campaign matters so much. Parker provides perihelion baseline data, Hubble tracks evolution over time, Europa Clipper delivers composition. Ground-based telescopes add spectroscopy and long-term monitoring. Breakthrough Listen rules out certain exotic scenarios. Theoretical models synthesize all of this into coherent explanations. Together, these efforts are building a comprehensive understanding of 3I Atlas. The shadowside jets remain mysterious, but they're not inexplicable. With enough data and rigorous analysis, the scientific community will converge on an explanation that accounts for all the observations. That explanation will deepen our understanding of comets, interstellar objects, and the diversity of materials in the galaxy. It will refine our models of thermal physics and volatile chemistry. It will inform future observations of similar objects, and it will remind us that the universe is endlessly instructive for those willing to look carefully and think deeply. So here we are, at the end of our journey through the mystery of 3I Atlas and its impossible jets. We've examined what Hubble saw in those December images. We've explored the physics that makes shadowside jets so puzzling. We've followed Avi Loeb's analysis and seen how multiple spacecraft confirmed the phenomenon from different perspectives. We've considered what rotation reveals about internal structure and what the broader implications are for our understanding of interstellar objects. Now let's pull it all together. What do we know for certain? 3I Atlas is rotating every 15.5 hours, causing its jets to appear to wobble from our viewing angle. It has at least 2 distinct jets streaming from opposite sides of its nucleus. After passing its closest point to the Sun, when the hemisphere that had been receiving maximum heating rotated into shadow, jet activity from that region continued rather than shutting down as standard models predict. This shadowside activity is the core mystery. It violates the simple equation of solar heating driving sublimation. It tells us that something more complex is happening, whether that's unusual composition, sophisticated internal structure, unexpected thermal properties, or some combination of all three. The potential explanations we've discussed all remain on the table. Subsurface volatile reservoirs could be venting through fractures regardless of surface temperature. Super-volatile ices like carbon monoxide could maintain activity at temperatures that would freeze water solid. Thermal inertia could be higher than expected if the nucleus has insulating layers or unusual material properties. Each explanation is plausible, each is natural, each requires more data to confirm or refute, and that data is coming. Spectroscopic observations will reveal composition. Long-term brightness monitoring will track how jets decline with distance. Computer models will test various internal structures. The scientific process is methodically narrowing the possibilities, moving from mystery toward understanding. But even as we pursue those specific answers about 3I Atlas, there's a larger story unfolding. This is our third confirmed interstellar visitor, and each one has taught us something different. Oumuamua showed us that not all interstellar objects fit our expectations. It defied simple categorization and sparked debates that continue today. 2I Borisov reassured us that some interstellar comets do behave like solar system comets, looking and acting exactly as we'd predict. Now 3I Atlas is showing us that even when an object seems familiar, jets, coma, comet-like appearance, it can harbour surprises that challenge our models. It's a reminder that the galaxy is vast, that stellar systems are diverse, and that our single solar system provides an incomplete sample of what's possible. This matters profoundly for how we think about exoplanets and astrobiology. If we're going to understand worlds orbiting other stars, we need to appreciate the full range of materials, chemistries, and processes that occur in different stellar environments. We can't assume that what we see around our Sun represents the universal template. Nature experiments across hundreds of billions of stars, and that experimentation produces outcomes we haven't imagined. Interstellar objects are messengers from that vast laboratory. They're direct samples of material formed elsewhere, carrying information about conditions in other stellar systems. They're probes we didn't have to build, visitors arriving unbidden to teach us about the broader galaxy. Every interstellar visitor is therefore precious. Observations are fleeting. These objects pass through quickly, fading as they recede into interstellar space. We have limited time to gather data, to measure composition, to analyze structure. Every observation matters. Every spectrum, every image, every data point adds to our understanding. The December Hubble images of 3I Atlas are part of that precious dataset. They document behavior that will be studied for years. They raise questions that will drive research and theory. They show us nature doing something unexpected, and that unexpectedness is an invitation to learn. Avi Loeb's analysis exemplifies how scientists should engage with anomalies. He doesn't claim to have all the answers. He presents observations, outlines possibilities, and calls for more data. He's willing to ask unconventional questions while maintaining scientific rigor. He reminds us that extraordinary observations deserve thorough investigation, not premature dismissal. Most of the scientific community expects that natural processes will eventually explain the shadowside jets. History suggests this is the most likely outcome. When nature surprises us, it's usually because we haven't fully understood natural mechanisms, not because we've encountered something artificial or exotic. But the process of investigation is valuable regardless of where it leads. By taking the anomaly seriously, by gathering comprehensive data, by building better models, we advance our understanding, we refine our physics, we expand our knowledge of chemistry and thermodynamics, we become better at interpreting the cosmos, and we maintain humility. The universe is under no obligation to conform to our expectations. It has surprised us before: pulsars, quasars, exoplanets, dark energy. Each surprise initially seemed impossible or inexplicable. Each eventually led to deeper understanding, but only because scientists remained open to the possibility that their current models were incomplete. 3i Atlas is offering us another such opportunity. The shadowside jets are a puzzle. The rotation and jet structure reveal complexity. The multi-spacecraft observations confirm this isn't instrumental error. All of this together says, pay attention, something interesting is happening here. As 3i Atlas continues its journey away from our Sun, it will gradually fade from view. Eventually, it will pass beyond even our most powerful telescope's ability to observe it. It will return to the darkness between stars, resuming its wandering through the galaxy. But the data will remain. The images, spectra, Kersen and measurements will be analysed for years. Papers will be written. Models will be refined. Understanding will deepen. And perhaps, years from now, when another interstellar visitor arrives, we'll be better prepared. Better instruments, better models, better questions. Each visitor adds to our knowledge. Each is a gift from the cosmos, delivered to our doorstep for inspection. 3i Atlas brought us the mystery of jets that shouldn't exist but do. It brought us evidence of complexity we hadn't fully anticipated. It brought us questions that will drive research forward. That's the wonder of science. It's not about having all the answers immediately. It's about having the tools, methods, and curiosity to pursue answers systematically. It's about being comfortable with uncertainty while working to reduce it. It's about looking at data that doesn't fit our expectations and asking, what can this teach us? Rather than, how can we make this fit what we already believe? The December images from Hubble captured jets emerging from shadowed surfaces. Those jets are real. They're happening. They exist in defiance of simple models, and they're teaching us, slowly, methodically, through careful observation and analysis, that nature is more creative, more subtle, and more surprising than we give it credit for. If this investigation into 3i Atlas has sparked your curiosity, I want you to stay with this story. Subscribe to this channel right now for updates as new data emerges, because this investigation is ongoing and answers will continue to unfold. Hit that notification bell so you don't miss the next development in this mystery. Share this video with anyone who appreciates cosmic puzzles and the beauty of the scientific process at work. Drop a comment below and tell me, what explanation for the shadowside jets do you find most compelling? Are you leaning towards subsurface volatile reservoirs, supervolatile ices, thermal inertia, or do you think there's an explanation we haven't fully considered yet? I read every single comment, and your insights often spark the best discussions and help me understand what topics to explore next. If you want to dive deeper into the science of interstellar objects, I've put together a playlist in the description below covering everything we know about Oumuamua Tui Borisov and the ongoing search for these cosmic wanderers. There's also a link to Avi Loeb's actual analysis article, so you can read his full reasoning in his own words. The universe is vast, it's strange, it's beautiful, and every so often it sends us a visitor that reminds us there's always more to discover, always more to question, always more to learn. 3i Atlas is one of those visitors, and we're privileged to be alive in the era when we can study it. Thank you for watching. Thank you for caring about science, mystery, and the endless wonder of the cosmos. Keep looking up, keep asking questions, keep following the evidence wherever it leads. The jets that shouldn't exist are still out there, still flowing, still challenging us to understand them, and that challenge is exactly what makes this journey worthwhile.